Hi, this is Roger from Kanka Labs, and today the third and final episode of our video series about using a spreadsheet for calculating the properties of magnetic antennas, and also the episode where we will reach the limit of our spreadsheet. Today it's about Ferrite-Rod or loopstick antennas, and these, however you want to call them, spiderweb or spiral antennas. And let's start with the loopstick or Ferrite-Rod antennas. And first of all, let's explain why we now come to the limit of our spreadsheet. First of all, here at the upper end, you can see a typical AM antenna for long and medium wave reception. This one here is the coil for the medium wave range, and here you can see a coil with many more windings, especially with many layers above each other for the long wave range. That's because, of course, you need for the lower frequencies of the long wave range, you need more turns, and you only can get this on a short Ferrite-Rod with multiple layers above each other. And that's the first limitation. Our spreadsheet cannot deal with multiple layers. It is only designed for single layer coils, like here the medium wave coil. And the second limitation is the properties of the Ferrite-Rod material now come into play, especially what's called the μr, the relative permeability. And this is not a constant. I will show you in a second a graph which I already presented to you in a separate video about this special shortwave Ferrite-Rod, which you can see is made totally different than the ones for the medium and the long wave range. Anyway, even if you have a good data sheet for your ferrite material, that would be the first thing you need just to get the so-called μr factor. The relative permeability, the μr, is a material constant, but the effective relative permeability depends first of all on the aspect ratio of your Ferrite-Rod. Here you can see a graph from exactly this material from Ferrox Cube. It's 4B1 or 4B2. And here you can see you first of all need the length to diameter ratio, which in this case is around 18, which means the ratio between the length of the rod and the diameter of the rod. And you can see if we now look up in our graph, we have an initial permeability of 250. That would be here. But with an aspect ratio of 18, this is diminished around to somewhere around here, so to around half its original value. So the first factor is the aspect ratio, and if you don't have such a graph, it becomes quite difficult to use the values in our spreadsheet. And the second is the position of your coil on the rod is also important. It's not only the number of turns and the length of the coil, but a well-known fact with Ferrite-Rod antennas is you can fine-tune the inductance just by shifting it. You have the greatest inductance if you put the coil in the middle of the rod, and it becomes progressively smaller if you shift it to the outer edges. So ferrite rods are really difficult to work with when it comes to calculating the necessary number of turns or the inductance of a given coil. And there is a third factor, or even more than a third factor, the permeability, which is essential in calculating the coil. First of all, it here has plus minus 20%. Well, that's okay, we can deal with that. But it's also temperature dependent, quite largely. And so, and the last factor is what we basically want to gain with our spreadsheet is the Q factor. And I've also made a separate video, which I'll give you the link below in the comments. And if you click here up on the right, I will make a little link for directly accessing the video about the magnetic losses. Well, anyway, magnetic materials have losses which can be much greater than the ohmic losses due to skin effect and proximity effect. And there is also a graph for this, so it's frequency dependent. For example, this material is only usable up to, let's say, 3 or 4 megahertz, and then the permeability starts to drop, and the losses is the distance between here these two graphs, increases, and the absolute maximum that you can use this material here is perhaps 10 megahertz, but I would not try to use it with the expectation of a high Q factor above 5 megahertz. So anyway, ferrite-rod antennas are quite difficult, and we really get to the limit of what our spreadsheet can do for us. So let's make 2 or 3 experiments still and then go over to our spreadsheet. So as a first experiment, let's try to verify that the inductance of a coil on a ferrite-rod is position sensitive. Now I've put it nearly exactly in the middle, and we get an inductance with our LCR meter of around 500 microhenry. And now I will pull the ferrite-rod slowly so that the coil moves to the outside section, and you can see that the inductance is dropping. First of all, not to a very great extent, but the nearer I come to the end of the ferrite-rod, then it starts to drop quite drastically. So this is a well-known fact, and it's in fact used for fine-tuning the inductance of the coil, and that way in an LC tank circuit the resonant frequency at the beginning or at the end of your range. So that was the first thing, and now let's make a second experiment with our shortwave ferrite-rod antenna. So you might notice some special things in this shortwave ferrite-rod antenna. First of all, you can see that there is a little plastic foil between the ferrite-rod and the coil, the winding itself. You should always have a separator and never wind directly onto the ferrite-rod. That is first of all for not to damage either the insulation of your copper wire or of your Litz wire, because the ferrite rods can be have relatively sharp edges. And the second is to minimize losses. When they are in direct contact, you could have an increase in losses. And of course, what you notice is the result of what we learned in the other 2 videos. Just at the higher frequencies, you have to use either very thick copper wire or and not Litz wire anymore, or even copper tubing. Now copper tubing would, the space here wouldn't be sufficient to use copper tubing, so I've used I think 1 millimeter or 1.5 millimeter copper wire, and that there is a great separation between the turns. That is just to minimize proximity effect. But there's a nice little trick just to fine-tune the inductance of coils that are wound in this way with thick copper wire and with a great distance. We have at the moment 3.37 microhenries of inductance, and now let me squeeze a little bit the winding and see if our LCR meter still gives a value. I might have disconnected now. So I had to change to a 10 kilohertz frequency, and now we have another a changed inductance. And let me pull it out again. Let's see if we see it now directly on the display. You can see that the inductance changes just by squeezing or tying or drawing at the ends of the coil. And that's also another well-known method of fine-tuning the inductance of coils, no matter if they are wound on a Ferrite-Rod or in air, just to fine-tune the inductance or the resonant frequency of an LC tank circuit. So, and because we have the full data sheet for this Ferrite-Rod material, we'll go in with the values of, just put it in so that you can see it a little bit better. We go with the values of this little shortwave Ferrite-Rod antenna into our spreadsheet. I'll give you the data now. The rod has 150 millimeter length. It has a diameter of 8 millimeters. We have, let's count it, 1, 2, 3, 4, 5, 6, 7 turns, and the length here of the winding now is around 8 centimeters, and the effective permeability, the relative permeability, is around 120, and we saw that the inductance should be measured in the range of 3 microhenry. And now let's check if our spreadsheet really gives this value. So one final word about Ferrite-Rod or loopstick antennas. Why do we use them at all if they introduce additional losses? You know from the other videos that we already have to deal a lot with skin effect and proximity effect, and we have taken every measure to counteract them, like using thick wire, separating the single turns from each other by great distances, etc., etc. Now, why do we then use Ferrite-Rod material? Simply because they get much smaller. Compare this little loopstick antenna with a spiderweb or a spiral wound antenna of nearly the same inductance, which is much larger already, and we can see the effect just by pulling out the Ferrite-Rod. With a Ferrite-Rod, this coil has an inductance of around 154 microhenries, and when we pull it out, it only has 13 microhenries, so more than a factor of 10 less, or in other words, we can make our antenna around with this material around 10 times smaller than, and you can see the size difference. So the reason is just a practical reason. If you need or want a small medium wave or long wave antenna, you usually go to Ferrite-Rod antennas and take the additional losses into account and live with them. But anyway, sometimes smallness is better or necessary than having such a much larger antenna or even a frame antenna. So the simple reason is the size factor. So this time we don't want to calculate the necessary inductance for a given frequency and a given capacity. We just want to check. We already know the inductance of our coil, which is rounded 3.4 microhenries, but later for getting an impression of the skin effect and the proximity effect, we should input the frequency. Let's say we want to use this Ferrite-Rod antenna for the short wave region around 5 megahertz. And now comes the main difference to our former examples. Now we in fact have to input the μr, and we have seen the effective μr from our graph was around 120 for this material and this aspect ratio of our antenna. Now, the next thing you have to watch out for, the diameter of our Ferrite-Rod is only 8 millimeters, but when we wind with 1 millimeter wire, then the diameter of our solenoid coil is in fact 1 millimeter larger, so it kind of hovers 1 millimeter above the Ferrite-Rod, and we have to input the winding diameter as 9 millimeter, because this is the sum of the diameter of the Ferrite-Rod plus the diameter of the wire. So next, the length of the winding was 80 millimeters. The shape of the winding is round or circular, and we get a number of turns for 5.46, so not near to 7. And you might think, well, where does the difference come from? We have the exact values of the winding diameter, the length of the winding, etc. Well, there are two effects which are not taken into account by our graph to find the effective permeability. First of all, because our solenoid coil hovers 1 millimeter above the Ferrite-Rod, this further influences the μr. And the second is the winding, although it is centered on the Ferrite-Rod, it goes to nearly to the end of the Ferrite-Rod, and we have already seen when shifting a coil on the Ferrite-Rod, the permeability and the inductance that you get smaller when you get to the end of the Ferrite-Rod. So in this special case, because the winding spreads over a large part of the length of our Ferrite-Rod, our effective μr factor from our graph must be further diminished. And here you can see we have to now try out, let's input 80. So with 80 we are already near to 7 turns, 6.68 when we are not rounding it. So it's still smaller. With a μr of 75, we now get near the exact value. But this is a good example that even if we have the full data sheet and take into account the aspect ratio of our Ferrite-Rod, then it's more of fiddling around with the value to get the effective UR. So it's better to make a test winding, measure it, and then either squeeze the winding together or draw it, spread it out over a larger area, or make a test winding with I don't know, 4 or 5 turns, and from that on just determine how many turns you really have to make to get your desired inductance. So you can see with Ferrite-Rod our spreadsheet is not exact anymore, but finally let's check and we cannot take into account the magnetic losses, which are frequency dependent, which are material dependent, but we can at least take a look at if we input the number of wires as 1 and 1 millimeter diameter, we can at least take a look at with the chosen wire diameter and the chosen distance between our turns, what effect does skin effect and the external proximity effect. Now the DC resistance is 4 milliohms, so that can be neglected, but the skin effect increases this to 0.07 ohms, including already the DC resistance. And because we have spread our winding over a very large length, the external proximity effect nearly has no effect. So that's one of the secrets, just to counteract the external proximity effect. Take a large distance between the turns. And of course we don't have any internal proximity resistance because we don't use Litz wire. And we are reaching at a theoretical Q factor of 1800, so that's very good if there wouldn't be the additional losses. And if I find the time, we will experimentally determine the true Q factor of this shortwave Ferrite-Rod antenna at perhaps at different frequencies, 1 megahertz, 3 megahertz, 5 megahertz, 10 megahertz. It depends really on that I find the time to do the measurements and make a video out of that. So anyway, the result is it's better to make a test winding. If you know your necessary inductance for your application, then just make a test winding, measure the inductance with an LCR meter, or there are other devices where you can measure inductance, like the small transistor testers or semiconductor testers, which I also made a video out of about. They also can measure inductance for very low prices. And so that was part 1 about what can we do with our spreadsheet with Ferrite-Rod antennas. So now let's finally come to these spiderweb or spiral wound coils. Now they are also a little bit difficult to use in our spreadsheet. The reason is, if we have a solenoid winding as we had until now, then we have the property of the length of the solenoid and the diameter of the winding. But here we have something different. We don't have a solenoid winding, but we have a spiral winding with, first of all, an inner diameter where the winding starts. So let's call this di. And then the winding goes spirally outward, so the diameter enlarges progressively and finally reaches an outer diameter of D, let's call it DO for outer. And then we have the, well, how shall we call it? The size of the winding. Let's call this with a small d. Well, this does not look, we have totally different designations as in a solenoid winding. And let's see how we can deal with that in our spreadsheet. I'll give you the data for this medium wave coil. You can already read the inductance, 170 microhenries. And here we have, I just have to look it up. First of all, we have 40, the number of turns is 48. Then we have an inner diameter of 42 millimeters, an outer diameter of 62 millimeters, and consequently the, well, how shall we call it, the size of the winding is 10 millimeters. Perhaps I'll find a ruler just to show you this. So the size of the winding is around 10 millimeters. The inner diameter, the radius is 21 millimeters, so the diameter is of course the double of that, 42 millimeter, and the outer diameter is 31. The radius is 31, so the diameter is 62 millimeters. And well, now there's one thing you should know. The inductance of the coil goes with the area of the winding. Now this area of course changes, and because the area goes with the square of the diameter, we'll just try not the arithmetic mean between the inner and the outer diameter. That would of course be 52 millimeters. But because the area goes with the square of the diameter, we take a value nearer to the outer diameter. Let's choose as an average value 55 millimeter as the average diameter of the winding. And then we take as the length of the winding, we just try out to take, well, the size of the winding, which here is 10 millimeters, and we'll go with these values into our spreadsheet and see if this gives any meaningful result to reach at a turns number near 48. So now let's again go into our the spreadsheet with our values. Again, we already know the inductance, and we want to see if with our given values we reach at the same number of turns that I have made. UR of course remains as 1, although the spiral wound coil is not wound in air but on special plastic, but plastic has no ferromagnetic properties, and so it's like air or vacuum. So we set the winding diameter should be set nearer to the outer diameter, so we made a guess at 55 millimeters. As length of the winding, we choose 10 millimeter, the difference of the radius from the inner to the outer end. the shape of the winding, well, it's a polygon, so it's neither square nor circular, but it's near to circular than to square. And we get a number of turns of 44, and the reality was 48, so this is at least within 10% of the true value. So what you should do in practice is just if you try to determine the necessary number of turns to reach for a typical medium wave reception coil 170 microhenries, you should just do 20% more turns as a test, which would be here 52 turns, then measure the inductance, and then rewind, or I don't know the exact expression. You just take some turns off until you finally reach at 170 microhenries. Remember always that the inductance goes with the square of the number of turns. So adding 10% of the turns increases your inductance by 20%, or in the other way around. If you measure your inductance as 20% too high, you should not take off 20% of the turns, but only half of that value, 10%. So I hope this became clear. Always remember, inductance goes with the square of the turns. So now we try to make a Q factor calculation, but there we have to watch out for some little details. First of all, in the spiral wound coil that I did show you, I used 16 by 0.07 millimeter Litz wire. And now there's another factor you have to watch out for, the so-called fill factor for Litz wire as 0.5. That is simply, if you look at Litz wire, you cannot simply add up the diameters. You cannot say, well, the total diameter is 16 times 0.07 millimeters. That gives a totally wrong result. You should compare here the diameter that you measure with a how is it called, a caliper or caliper, with a true value, because you still have the insulation. There's usually a silk outer insulation on Litz wire. And so compare this, and if there's a great deviation between the calculated value and the measured value, just manually input this here. And there's another thing. With these special spiral wound or spiderweb coils for taking into account or calculating the external proximity effect, remember that because there is an uneven number of slots, that means only every second turn is again on the same side. So the distance between each turns, they are not lying as in a solenoid coil, turn near turn or turn to next turn. There is a separation of double the diameter. In our case, if we have 0.6 millimeter diameter, you have in fact from the distance between one turn to the next is 1.2 millimeter, double the value of the diameter of your Litz wire. I hope I will try to put a little drawing in the background so that you can imagine what I mean with this. Anyway, DC resistance doesn't interest us. It's relatively high as 2.1 ohms, but this is not so bad. Anyway, the skin effect again does hardly play any role. The skin factor, which gives you the increase of the DC resistance, is only 1.03, which means we only have a 3% increase of the DC resistance because we use Litz wire. If you would use a single wire, this would look totally different. So skin effect does not come into play. But now here comes the part where the values that we did input gives us wrong results. The external proximity effect between the turns here is even smaller, and this is of course wrong. It must be greater than the resistance only to the skin effect. The factor 0.9, that would be nice if we could diminish with a spiral wound coil the external proximity effect. So this is wrong because we kind of interchanged, where do we have it, the winding diameter and the length of the winding. That's here a little mix up, or I don't know how to really call it. But what again, although it's experimental, we can see the internal proximity effect due to using Litz wire, so between each strands of our Litz wire. That seems to be the dominating effect, and this increases the ohmic resistance, already including the skin resistance, from 2.16 to 7.28 ohms. So we basically don't have to care about the wrong external proximity effect, because the internal proximity effect seems to be the dominating factor, and this gives a Q factor at 1 megahertz with this special type of Litz wire and with the dimension and number of turns of 146. And I already once have measured this coil, and I think I can remember that it was somewhere between 100 and 200. I even think it was nearer to 100, so even a little bit worse than we get here. If I find the time already here, I will make a comparison measurement between a Ferrite-Rod medium wave antenna, a spiral or spiderweb coil, our frame antenna, just to see what is really the best antenna and how good our indication here of Q factor from our spreadsheet, how near it is to reality. But this is sometimes these spiderweb coils are really given with extremely high Q factor values, but that might be true concerning skin resistance and even concerning external proximity resistance. But the people who made this extremely high values of Q factor, they usually do not take into account the internal proximity effect in the Litz wire, and so I think we're quite near to the true values we get in reality. So as a final effect, let's try if we can change our values here so that we can evaluate the external proximity effect. So for finally getting an impression of the true external proximity effect, we just have to manually change the winding density. Here you can see as an explanation, if we have one, that would be touching turns, which means that really there is one turn next to another. We know that in spiral wound coils, and if you can see here, if the value is greater than 1, that cannot be true in reality, because nearer than touching turns is impossible. But on the other way, if we take manually a value of 0.5, that would come near to how a spiral wound coil really is, because the true distance between each turns is about a ratio of 2 to 1, or 1 to 2, depending on how you look upon it. So let's input manually a value of 0.5, and now we can see the external proximity effect is in fact again slightly larger than only due to skin effect. So this comes again nearer to reality, and our Q factor has gone down a little bit to 138, and my guess is this is very true or very near to the real values, and I'm really hoping to find the time to make a real determination with the coil that we have calculated here. Finally, let's just for demonstration change the frequency to see or to demonstrate that the Q factor, how much frequency dependent is. We go to the lower end of the AM medium wave range, that is around 500 kilohertz, and we see the Q factor has gone up, has gotten a little bit better to 183, and now let's go to the upper end at 1500, or in the US it's even 1600 kilohertz. So let's take the European end of the medium wave range, 1500 kilohertz, or in other words 1.5 megahertz. And there we can see the Q factor has dropped to 91. So you can see how much the frequency comes into play, because all these factors, except for the DC resistance, but the skin effect, the external and the internal proximity effect, they are all frequency dependent. And so I think we've gotten some useful results. Anyway, you can see due to the special kind of winding, the problem is here, this is not, at least at this point, it's not fully implemented to calculate spiral wound coils exactly with this spreadsheet. But anyway, we can get relatively near with some little tricks how we interpret the winding diameter as somewhere near the outer and the length of the winding as simply the difference in radius between the outer and the inner radius. And we even can kind of simulate manually the special type of winding where one turn is on the front side of the template, of the winding template, and the next winding is on the back side. That's one of the tricks of spiral wound coils, just to increase the distance between the turns, and therefore we get a relatively near to reality calculation of the external proximity effect. So you can see this was not so easy as with our frame antennas and our single and multi-turn loops. You just have to know what you are doing, but you get some useful results at how many turns you have to do and what Q factor you can expect. So we should, as the diameter of the winding, we take a value near to the outer diameter. Now there's one problem. When you don't know beforehand how many turns you are doing, you don't know where your outer diameter is. So it's also a little bit of experimenting. We only know the inner diameter. That's just the end of the slots here where you start your winding. That is fixed. But the outer diameter, of course, depends on the thickness of your Litz wire and the number of turns. That determines your outer diameter. And then we take as length of the winding, we just take, which is also not known beforehand, the difference between the outer and the inner diameter. In our case, or to be correct, the difference between the two radiuses. And so this is not very satisfying, but it gives you at least a starting value, and then you make 20% more turns, measure it, and finally reach at the correct value. I also will try to give you, there are of course exact formulas for spiral wound or spiral wound coils, but they are not implemented in the spreadsheet. Perhaps I can find them anywhere and make an extra spreadsheet. Anyway, there are some graphs. I'll give you the link to the graphs where you can better determine the number of turns at a given winding template like this here. Just to have a better starting value than guessing around. So as you can see, we've again reached the limit of our spreadsheet, what we can really do with it. But anyway, we got the result that although this spiral wound coils are in theory give a very good Q factor with the right Litz wire, but again the internal proximity effect in the Litz wire, this ruins our Q factor, or at least it makes it much worse than if we only would take into account the skin effect and the external proximity effect. So that was it for today. Not 100% satisfying, but I told you at the beginning, this is with these kinds of coils with ferrite-rods, antennas and spiral wound coils. The spreadsheet was not designed originally for these. It was basically or originally designed just for doing frame antenna and single and multi-turn loops. But anyway, we get some useful result, although they are not 100% consistent with reality when trying to calculate the properties of ferrite-rod and spiral wound coils. So that was it for today. I hope you liked it anyway, although the results were not so great as in the first two episodes. So hope to see you next time. Bye from Roger, bye from Kanka Labs. Until next time.